Hello, my name is Ben, Alpha Bravo 4 Echo November if you're a ham radio operator, and this is Stray Capacitance. I've decided to start a channel and do a little streaming, mostly of projects that I'm working on or things that I think other people might find interesting. I certainly don't expect this to be a big success, but I thought it might be fun. So today I had a few things I wanted to go over. For starters, this is mostly a test recording just to see how the audio works, what it picks up and what it doesn't, and what works well in terms of video quality and things like that. So I have a couple projects I wanted to talk a little bit about, but first a little bit of an unboxing. A box from DigiKey arrived today, and some stuff is interesting and some is not, but I'll just go through it real fast. First is a bag full of op amps, the OPA 1678s, which I'm going to be using in a project we're going to be talking about. Nice little strip of them there. I got about 15. I should be using about 4 in the project, but I always give myself some extra inventory for future projects and for when I inevitably screw up. As part of that project, which we'll be talking about here shortly, I've got a bunch of different pots. The project that I want to talk about in a little bit is a small EQ for amateur radio operating. One of the aspects of amateur radio I really enjoy is getting outside, so I like to operate portable when I can. Parks on the Air has been my primary mode of operating. I want to do some SOTA as well, Summits on the Air, but I haven't had time, and I live in the Midwest, so snow-capped mountain peaks aren't exactly readily available. But there are some things around, a couple hours away, so I hope to do those someday. And I've found in operating my radio, which is a Yaesu FT891 that you can't see right up there, that the EQ settings in the Yaesus are buried. So it's stereotypical Yaesu that everything's buried in a menu. And this radio I've been very happy with, but it does have a limited selection of controls on it. So I'm hoping to do some EQ for receive to help me pull things out of the noise. It's part of a larger project where I designed and built this board, and I don't know if you can see it, and bodged it up in a couple places where I screwed up the design. But this board is an adapter from the Yaesu mic connection and audio out with some biasing circuitry so that I can run a standard tip ring sleeve style 4 connector headset for your cell phone as the audio, as the headset and the mic input. And then this connection here just becomes a simple push to talk button like this, also just using a tip and sleeve connector. So this allows me to mostly keep my hands more free than they would with the mic that comes with the FT891, which is a standard handset mic, and this lets me keep my hands on my cell phone where I run some logging software I'm working on. So when I built this, I was thinking ahead a tiny bit, and you can see a set of 2x4 pin headers down here at the bottom, and I've got some colored jumpers on there just to keep my things straight in my head. But I thought that this might make a good place for me to do breakout boards, shield boards over the top of this. And the EQ is going to be one of those. So it will have the 2x4 pin header on the bottom and slot over this and hopefully be pretty small and compact. So in an effort to drive that, I initially thought I wanted to use slide pots like this. I happen to have some of these. Like a lot of electronics people, I enjoy ordering random things off eBay and seeing what I get. So I had some of these in my box, just for scale here. Here's my favorite ruler. Hopefully I can get it to not glare too badly. So these are about 50 millimeters long end to end and have about 40 millimeters of travel. And these happen to be 100Ks. Not that that's important. You can design the circuit however you want. And I initially thought I was going to use 3 of these. if you're not an amateur radio operator and you're operating single sideband, which is the normal voice mode. Single sideband only has a bandwidth of about 3 kilohertz. So compared to an EQ that you'd use for music that might go up to 20 kilohertz if you're still a young person and have good hearing, you might hear up that high. So this is a much narrower bandwidth. So if I went and bought an EQ, many of them would fit that entire 0 to 3 kilohertz range behind exactly one knob. And that's not good enough. I kind of want to be able to drop the low end out or the high end out, depending on where the noise is, especially where I'm at. I'm very close to a 5,000 watt AM radio station, and it's quite noisy, so I get a lot of interference when I'm listening, and I want to be able to kind of tune that out. So this was my initial thought, but if you look at this, fitting 3 of these side by side here doesn't leave me with much space, and I can certainly make the profile of this circuit board bigger if I want, but compactness is a virtue for sure in amateur radio. That's one of the reasons this circuit board I made small enough that it was slightly a pain for me to put together. So it works entirely well, and I'm completely happy with it, but I'm trying to keep that kind of small, compact form factor. So I ordered some 10K circular pots, right? Nothing particularly special, but an interesting aspect to this is that when you're operating outdoors, you're frequently operating outdoors. So I was talking this project over with a friend who's also an amateur radio operator, and he pointed out that I should try operating these with gloves on. So I thought that was brilliant, and the pots that I had seen previously, which I was kind of taking as my reference material, were off a fun little project from a company called Teenage Engineering called a Pocket Operator. And this is just a little slick sequencer. And they've got a bunch of different ones, and they all have different names and slightly different sounds. I find this one really fun. I'm not a musical person, but I had a lot of fun with it. So I saw the pots on here and thought that they were perfect. You read a few reviews, and a lot of people have actually had to replace these on their pocket operators, so maybe not these exact models, but something similar. And then I was over at my friend's place, and he suggested I try this with gloves on. So I put on one of the pairs of gloves that I wear when I'm out operating a lot, and these became really fiddly. It's really hard to tell where you're at in the range like this. And I don't need a ton of feedback. This is definitely going to be tuned by ear. But I wanted a little bit more than this. I can't tell if I'm turning it or if my fingers are slipping or whatever. So I did what any self-respecting person would do, went on DigiKey and ordered a bunch of different pots. So all of these today that I've got here, let's get the pocket operator out of the way, as pretty as it is, are 10K linears. I believe they're all linears. I think I got any logs. I wanted a straight up apples to apples comparison. Not that the taper would make any difference in the feel, but I thought it would be interesting. So I think there's 2 different brands here, as I recall, and I'll leave the part numbers up there, but I'm not going to go ahead and look up the parts or anything. My only goal for today is to think about which of these feels nice, because I need to know what footprint to use in the circuit board design. And I think these are all interchangeable, more or less, with the possible exception of one, which I thought was oriented upside down to the others. But let's see. So let's set them all to minimum and see if the indicator notch is in the same orientation, and it looks like it is. Looks like I was mistaken, which is cool. That means I can go ahead and pick this footprint, and these should be identical across everything. So that'll be handy. Means I can go ahead and start on that design work. But there's still the question of which ones to order. They all feel pretty good. That one's got a little resistance, but and compared to this one, which has a longer shaft. Let's orient these in ascending order of shaft length, at least within this one brand. Huh? Might make a little more sense. So that feels okay. That one feels all right, but it's definitely hard to get a hold of even with bare fingers. I don't think I'm going to wind up with that one. This one I would definitely need to take into account in the design of the case. I haven't decided exactly what I'm doing for a case on these. So this shaft here is 16 millimeters long, 17 millimeters long, something like that. So that's quite long, and I think that that would present a snag point. This device in its little 3D printed sleeve sits on top of the radio and gets shoved in my go bag when I do go to the park. So a bunch of these sticking out on the top is going to present something to snag and possibly snap everything. So that's part of the equation here. The other part is what am I going to do for a top surface? An interesting option that a lot of people use and that you see from a bunch of people on the internet, Dave Jones of the EV blog or others, is to use a printed circuit board as the front panel of the device, which sounds like fun. I've not done that, and that would give me an opportunity to play around with some of the KiCad features for laying that out. But so there are those. Now these two over here are both very similar. Shaft length is about the same, and about the same compared to this one, which I think is the right shaft length. So I think I'm going to put these two to one side, and I'm going to rebag these just so that if and when I use these on a future project, I can hopefully find the part numbers and not struggle with that, which I've gotten to do in the past. So, move these into the shot. This one has a much coarser knurl on it and has a indicator notch that kind of is just a line inside of the pot itself. Not sure if that's going to show up. And I apologize for the camera. This is not the best setup, but it's what I've got to start. I'm not going to spend a bunch of money on an HDMI capture device for my good camera if I don't like streaming. So, this one's nice and has a good feel to it. It's got a little bit of resistance, but it's not bad. Completely doable. It does feel nice that it wouldn't be easily bumped. It wouldn't just all of a sudden turn the treble all the way up. This one has a little less resistance, and this one also has a detent. And I don't think that's important. When I ordered these, I didn't make that one of my criteria. It's not bad. I'm not going to reject anything for having a detent. But it's not a distinguishing factor to me. This one, just kind of garden variety. Feels fine. So, let's try the test that we came here to do. Winter glove, light winter glove, but I'm not planning on going out in the Arctic snow right now. That one, I feel like I've got a firm grip on. It's not, I don't feel like there's any risk of me slipping with that enhanced knurl. Well, the detent, it's actually takes a little bit of force to get it out of the detent in these gloves. Interesting. That's all right. I could certainly live with that. takes a little less force than this one, at least around the detent. But other than that, they're comparable. I think the choice between these two would be if I would want the detent or not. But I think right this second, I'm leaning towards this pot. And if it were that much proud, say the surface of the front lid came up to here, and it was only the knurls that was free, I feel like I could get a decent hold on that without a big problem. Alright, well that's some good information. So I'll have to think about that a little bit more, and I'll probably order about 3 more of these. So there will be 3 bands in the EQ that we can talk through here in a little bit. A low, a mid, and a high, and then a gain control. Nothing particularly complicated, but possibly interesting. One other thing I wanted to talk about, actually a couple other things before we move off the bench here and onto the computer. Couple of interesting projects perhaps. I have a brother-in-law who needs assistive technology. And his favorite trackball for a long, long time while he could use it was the Logitech trackballs, the one that is the M570 is the current version, right? Yes, that's what's on my desk, and I've loved the Logitech trackballs for a long time too. The Microsoft ones are also excellent, the thumb trackballs specifically. So this is the brains of a M570 or the predecessor. I can't remember exactly. And here's the trackball itself and the integrated sensor, right? This piece of flat flex used to go to there. That was the rough orientation of the whole product. And I'm interested in reverse engineering the protocol for this. It appears to be SDI, so shouldn't be particularly difficult, but there are a lot of very small pads on there. My ruler flipped over to inches. Heresy. And my soldering skills are not up to this task. I tried, and I tried to put little 30 and 40 gauge enamel wire on here to break this out. And the goal is to break these wires out, run them through a logic analyzer, and then onto the trackball so that I can see data flowing both ways. That's worked well for me in the past. I'm no expert reverse engineer, but that's what's worked well for me in the past. And for what it's worth, there are a few indicator numbers on these parts. I've got several of these trackball sensors, but none of them turn up anything that I can find on the internet. So I was able to find the part number for the flat flex connector, did a little Oshpark, obviously, order for the footprint, mostly to test my footprint. I'm not the best at building footprints, so I tend to do a test circuit board, and often I turn that into a breakout board, as you can see. So just 0.1 inch headers, and the trackball sensor itself, and we'll see how we go with that. The real goal here, as I said, is to reverse engineer this sensor, and I'm hopeful that a future version of the project I've made for my brother-in-law, which currently uses a joystick, lets him just use his thumb to drive his mouse around on his computer. It fits onto his wheelchair. Is able to use these trackballs, and I can find a way to mount that and let him use this, which should give him superior accuracy, but also speed, right? You can kind of decide how fast you want to move one of these trackballs. Plus, I've got some of the old red and black dimpled versions of these, where it's just a speckle pattern of dots, which I think look cool too. But the blue ones are also exceptionally nice. Wonderful trackballs. If you're ever in the market for a trackball, I love these. Well, as part of that project, getting this data out has proved challenging for me, at least. So I'm not, as I said, not good enough to really solder this. I did try on the bottom, there's the interface for what I presume is the JTAG and the programming of the Atmel that's on here. And that covers almost all the same pins. It covers the SDI bus. It doesn't cover the chip enable that's up here, but I could probably work around that. But I made a small bed of nails, 3D printed a holder for it, and that hasn't been very satisfying. I haven't gotten great results out of that. So what I'm hopeful is that I'm able to use a product that somebody, not a product, a project that somebody has put up on Thingiverse, and it uses acupuncture needles as probes. So I've 3D printed a bunch of these little arms, and scarily enough, you can just order acupuncture needles off Amazon. Wow, that's just going to drive me nuts. Let's indulge our tendencies for order here for a second. 5. There's one more. And then I've had several just off the printer. So the ASMR portion of this stream today will be when I hold these up here in a second and remove the support material. Actually, let's just go ahead and do that now. Let's see if the mic picks this up. Removing support material is incredibly satisfying. I know a lot of people take a lot of pride in printing without support material, but I mean, come on. That one didn't come off too clean. I'm going to have to go after him again. I'm sorry if your standard for ASMR in electronic streams has been set by someone like Micah Stott or someone else with a much better voice. For me, you'll have to live with my voice and 3D printed support removal. Get that stuff off the bench. So, a bunch of these little probe holders and these exquisitely sharp needles will hopefully let me probe this circuit board. There's a whole additional structure to these. There are arms that hold on to them, and they're adjustable, and then there's a frame that holds them, and they will come in hopefully and just probe these pads. They also hold the circuit board, and the needles are a little flexible, so you can apply a little pressure. I'm a little worried about the ohmic resistance of these. They measure, at least for me, this one measured at about 15 ohms, which isn't a huge amount for a digital signal that I'm going to run through a logic analyzer, right? As long as it's high enough, it's high enough. But might present some difficulty. So, I'm going to very carefully take the one that's got the needle in it and put it in a pin cushion, lest I become the pin cushion. I'm going to take the rest of these and set them out of the way, and set the trackball to one side. That'll be a future stream if anybody's interested, and if I get around to it. The reason I called the channel Stray Capacitance is there's not a lot of it. Much like my capacity for these projects, I don't have a lot of time. I'm an adult, just like a lot of us, and I don't get a lot of time or energy to work on these things. But thought it was fun anyway. So when I do get to work on them, maybe I'll stream. One more thing to talk about, just because I thought it was kind of interesting and somebody else might learn something. I needed a microphone preamp. I actually, from my brother-in-law, he gave me a Shure SM58. It's a very nice microphone. Makes me sound way better than the headset mics and the desktop mic I was used to using. But I needed a preamp, obviously. The signal on a dynamic microphone seems to, from everything I can find, everybody says it might be like 5 to 50 millivolts. Not quite line level. So I did a little thinking, put together a little circuit that's a very simple gain stage using an op amp. I've got these LMC 6482s in nice dip packages so that you can breadboard them up real fast. And I put this together, and it was horrible. It was terrible. And I got the scope out and probed it up for a bit. And obviously, you can see here, I threw a lot of decoupling capacitance at it. And I still just could not get a signal out of the thing. And I switched power supplies. And suddenly, I changed, of course, as any good debugger does, right? You change 50 things at once. You don't just change one thing. That would make it way too easy. But I changed many things. I rewired things. I figured maybe these long, terrible breadboard traces are picking things up. Not sure. And it wasn't 60 hertz hum. It was very broad banded. So I played around with it a little bit, switched my power supply out, spent a lot of time with the scope, a lot of ripple on the power supply, so I was chasing that, and that was one of the things that led me to switch my power supply. And in the midst of changing that and doing a bunch of other things, as I said, I had built an AM broadcast receiver. What is going on? I start off, just with a bunch of voice in my line out to the computer, and had no idea what was going on. Finally, I figure out, I get enough of it through the noise of the signal to find that it's a home improvement show, and you search, you take AM, talk radio, the kind of show, your area. Eventually I tracked it down, and there's a 5,000 watt AM broadcast station less than a mile from my house, which explains why on my FT891, and especially on my vertical antenna, I've got about an S9 noise level most days, sometimes 20 over. For those of you who aren't radio amateurs, that's a lot of electromagnetic noise. I always assumed it was from something in my house, but obviously not. But I started looking at the circuit and couldn't figure out where the noise was getting into it. I put a little shield over it, didn't help. Anything else. Started debugging, unplugged the microphone, still had the noise. Unplugged the line into the computer. There's no noise, right? So it's definitely coming from my circuit. Turned the power off. Still have the noise. I was shocked. I was sure that it was getting amplified by the amp, coming from upstream of the amp, going through the amp, and coming out as a strong signal. Not the case. It was certainly quieter without the amp involved, but I couldn't figure out where. Finally, I had turned the power off, but I finally pulled the power leads off the circuit board, and the noise went away. Interesting. So the power supply I was using at the time is one of these cheap little adjustable power supplies. You can get them off eBay. They're very handy, nice little things. I run mine off my amateur radio power supply, turn it on, hear everything click on, comes on. It'll run off a wide variety of voltages, but you can see there it's got 13.8 in from the good old Anderson power pole connectors, and I had it set to 5 volts, so it was putting 5 volts into the circuit. Everything was very, very noisy, so I was like, well, maybe it's just got a poor regulator. I mean, it's obviously a switch mode power supply. Nothing this big is going to be a linear supply, and it doesn't weigh 50 pounds either, so that's a good hint that there's no gigantic transformers in it. So I set it up to 9 volts and brought a 7805 in, a linear DC regulator, dropped it into the circuit. Still a huge amount of DC ripple, and radio stations still coming through clear as a bell. Finally, in debugging all this, when I unplugged from here, even if I unplugged the power line and just left the ground connected and this was off, like powered up but no output voltage turned on, it was receiving the local radio station. So I turned him off, put him away, and powered down my ham radio power supply, and switched back to where I had started, the Analog Discovery 2 from Digilent, which has a very nice power supply in it, as long as you don't want to go over 5 volts. I say very nice. It's still got a fair amount of ripple. And the ripple on the Analog Discovery 2 is what had driven me initially to go back to my supposedly bench power supply. I won't be using it for analog work any further. But that and a bunch of decoupling capacitance got me to the point where you're listening to me through this preamp now. So I can't turn it off, which is unfortunate, but it seems to work well enough. I've still got noise in it, and I do hope to improve that in the future. But partially that's just environmental noise, the HVAC and things like that. And partially that's noisy circuitry, because I'm an analog newbie. So if we haven't discussed it yet, something to take away from my streams is not to take much away from my streams. I'm learning. I am a software engineer, software developer by trade. I kind of hate the term software engineer. We don't take our jobs nearly seriously enough to call ourselves engineer. Every time you get a software patch that breaks something, if engineers behaved like that, we'd all be dead. Buildings would have fallen, our cars would have exploded, all those things would have gone horribly, horribly wrong. So I prefer software developer. We do develop software, and hopefully we develop our skills along the way. And this is just a matter of interest for me. I enjoy ham radio a lot, but I've always enjoyed electronics, mostly digital to this point, but amateur radio has gotten me very interested in the analog side. Obviously the little headphone or microphone adapter, headset adapter, and then the EQ are obviously going to be projects on the analog side of things. So that's kind of where I'm at today. And what I'd like to do is spend just a few minutes going over the design for the EQ board here, and then we'll see where we're at in the day. And probably in a later stream, I'd like to do a little KiCad design for the microphone preamp. If I'm not sure if I'm ready to spin that board yet or not, but I thought that might be fun to do. So let's switch over here. Just a second, because I'm back-footed, of course. And with any luck now, you are seeing my desktop. So I'm going to be amateur hour here, flash up OBS, make sure you can see my desktop in the infinite nesting windows of doom. Accidentally give you my local IP address. Hopefully that's not too shameful. Okay, so this is the circuit I've put together so far. I'll just kind of talk through it in stages, and then we can drill into each stage and kind of see where we're at. And again, I'm an amateur when it comes to the analog electronics side of things. If you've got feedback, if I'm doing dumb things, please let me know. I'm not going to be offended or upset. I appreciate a respectful tone. I'm trying, right? I've read, and I think that the whole internet really benefits from more respectful tones. Calling someone an idiot doesn't help. Hey, did you know there's a better way to do this? Is a great tone, and we could all benefit from using it more. So the pinout up here is taken from the board I showed previously. It's that little jumpered section down at the bottom that we talked about where I left some room for expansion. We've got audio in from the radio and ground and 5 volts. So that's one of our constraining factors here. The FT891's mic connector gives me 5 volts and ground. I don't have 12 volts. I don't have plus and minus 12 volts. I don't have plus and minus 5 volts. My rails for the op amps are going to be ground and 5 volts. So that is a limiting factor. I've learned a lot about op amps on this project, and one of the really interesting things are the power restrictions. If you're learning along with me and you're new to op amps, not all op amps can output their highest voltage or their lowest voltage. Some can, and they're called rail-to-rail op amps, and they have different limitations. Every op amp has bandwidth limitations. Luckily, on an audio project like this one, those aren't going to be very impactful because we're going to be well within the bandwidth of what any modern op amp can do. And also, they're going to have those power limitations, how close they can go to their rails. So if my rails are ground and 5 volts, and the voltage levels on the audio signals here are close to 5 volts peak to peak, very, very close. So to drive the headphones that I'll be using, which have an impedance something like 300 ohms. I'm guessing. I haven't measured it exactly. But that seems to be a pretty common number that people use. So I've got to be able to use pretty much that full range of ground to 5 volts. So I'm using a rail-to-rail op amp. That would be the OPA 1678s that I showed you earlier when I was unboxing things. So, back to our connector, we've got audio in from the radio. Amateur radio is single sideband and only uses one channel of audio. So stereo is pointless. So I broke it out from the upstream connector here, but I really wasn't thinking when I did that. On the downstream side, it's definitely useful because I'd like it in both ears. I'd like to be able to hear it in either ear or take one earbud out if I'd like. So that's why it was broken out this way, is I broke it out because the radio passed it in, but we're not going to use the right in here. We're going to take everything from the left in. We only need one set of EQs because we're only working on one channel, and we'll output the same signal to both the left and right. An earlier version of this project, an earlier ideation of this project, I should say, also was going to do some balance between these and allow another input. I occasionally use an SDR on my computer to receive on a different antenna than I'm transmitting on, and the idea for that version of this project would have let me put the computer's audio into, say, my right ear, the radio's audio into my left ear, and then speak into the radio. That may still happen, but I decided to cut scope a little bit. These projects can get vastly out of control and become uncompletable, and I decided to stop before I got that far. A bunch of comments to myself here throughout, and some to-dos. Actually, I can delete this to-do. Isn't that nice? I need to double-check this pinout before submitting the PCB, so big and bold up top. But the mic is going to flow out as it does right now. The goal with this version of this project is to still use the 4-pin cell phone headsets. There may be another version where I let myself plug this dynamic microphone in, and actually that's also on the cards. I'd love to be able to use this same microphone with the radio, because I'm very happy with the way it makes me sound, which is nice. So, we've got audio in and audio outs, and mic in and mic out. Mic in and mic out, those two pins will just be wired together. We've got ground and 5 volts, and some bulk decoupling capacitors, just for the whole board. Everything gets decoupled. You get a capacitor, and you get a capacitor, and then local decoupling closer to the individual op amps is closer to the individual op amps in the PCB. I'm not an old hand with KiCad, so, or KiCad, I'll probably pronounce it both ways. So, I wanted to keep everything close together. So, KiCad has this interesting way of dealing with op amps or packages that have multiple elements in them. So, and I didn't know this, which is why I'm mentioning it. When you look at a KiCad symbol, like this one, you set the library reference for it, and you add these by tapping A, and it will load everything. And I did an OPA 1678. Yes, that is an op amp. And you add it in, and it's got 3 units to it. And if you look over on the right, there's Unit A and Unit B, and they're identical, but they're the 2 different op amps that are on the same package. And then Unit C is the power supply side of that. So, we've got Unit A, Unit B, and Unit C here. So, Unit A is my audio input, and I'm just going to buffer that and run it through a quick little filter here to kind of stabilize the input a little bit and hopefully keep any RF out of the amplifier. This is in straight up voltage follower mode so that I'm not presenting a big load to the radio when I draw off of it on multiple op amps. Don't want to modify its output and don't want anything I do to this signal to screw up the radio. So we've got a buffered audio input coming out of this sheet. The other thing we've got is, since I'm between ground and 5 volts, I need to split the rail. I need to generate my virtual ground in between that, around 2.5 volts, for me to work with. And so there's effectively a filter here, right? A filter to positive and a filter to negative. And I was watching a stream by Smitty Halibut, doing a stream on a very similar project, which really helped me clarify a lot of my ideas and helped me work towards this. And he put his filter calculations right next to the components, and I love that. I'm going to start doing that everywhere. So these components on each side form a 16 hertz low pass filter. So anything higher than 16 hertz should get shunted either to ground or 5 volts, depending on which side of the rail it's on. And that's great. So this signal should be nice and stable. And then we've got another op amp in straight up voltage follower mode, so that we don't impede on this at all as we go through things. We just want a nice stable 2.5 volts, also known as audio ground here. And again, I'm decoupling it again to 5 volts and ground. 10 mics here, 1 mic up here. And then on the power supply side for this sheet, I've got the just a 0.1 microfarad cap to both across 5 volts and ground, so that any local noise in that power rail gets smoothed out. So that's our input and analog ground sheet. And there's only one of it. These others, I've used the KiCad subsheet functionality because there's 3 channels to the EQ, but they're all identical except for component values, which we'll see in a second. So we've got the low, the mid, and the high. We'll drill into the low, but literally they all point to the same sheet. So it takes its audio in, routes it through an audio filter, through a 10K pot, a 10K resistor, and the audio out. So if we backpack out here, each of those is just going to filter its audio, use the pot to trim the voltage levels, and pass the audio out. So all 3 of these are coming out, getting merged into one, and getting passed to the mixer sheet. Let's take a look at the audio filter. There are a ton of ways to filter signals, and I am learning. So don't take this as gospel or indeed a good idea, but this is what I'm doing. I've decided to use a 5 or 6 order active filter for this project. So each of these, this can be up to a 3 order filter at the top. This can be up to a 3 order filter at the bottom, using the 2 halves of an op amp. This says LM358. That's incorrect. These should also be the OPA 1678s. But I need to change that. Glad I saw that. Okay. So in an audio filter can be a bunch of different types, mostly low pass or high pass, and then you can build other filters from those where you stack up a low pass and a high pass and you make a band pass filter. The frequencies that are admitted by both are passed through. Or you can stack them up differently and rather than in series kind of use them in parallel, you use a high pass and a low pass and you make a notch filter that excludes a certain range of frequencies. So these are my calculations over here. I don't know what the right way to do these things is, so I just did it my way. Not to sing, and I won't sing for anybody. I decided that the elements going either to ground or in the feedback from the op amp would be called A for kind of active, and the ones in the signal chain would be called P for passive. That's not great because in a low pass filter, the active elements are active in that they're capacitors. But in a high pass filter, the active elements are resistors, which aren't really an active component. They don't change reactance as frequencies change. But the P's become the capacitors in a high pass filter. So you can see my calculations there. I won't go through them. If you're interested in this, Art of Electronics is excellent. I put off buying that book for far too long. I have not read it. I wish I had the time and dedication to get all the way through it, but I have not done that yet. I also have Practical Electronics for Inventors, which is also quite good. The filter calculations largely came out of Practical Electronics for Inventors, and I've been very pleased with how that's gone so far. So, ignoring the incorrect op amp there, I wonder if I can just change that here. Yay! 1678. Yes, I can. So we'll fix this now. Unit A. I wonder if I can just copy paste that. Can. Well, maybe it is not changing the value. Live typing. I know that's the most riveting kind of stream, and that's really what you were here for. At least I have a mechanical keyboard. Maybe that's providing some nice ASMR. So, now we've got the OPA 1678, A, B, and C. Yes. Question C. Obviously, I haven't annotated my schematics yet. That's one of the next steps. So, that was a drill into the audio filter. Here's the EQ channel, which is just that, plus a pot and a resistor. And then we'll look at our mixer here. Shock of shocks, it's a couple more elements of OPA 1678s. So we're looking at an OPA 1678 with two channels for the front end, kind of giving us our analog ground, which we've used throughout, by the way. It's all over the place, and it was all over the place on the active filters. So we've got our analog ground, which will be 2.5 volts reference to the actual digital ground that the radio is providing us, and our buffered audio input on that first sheet. So here we've got one OPA 1678. We've got three more here, one per channel, using both elements of each in there. So we're up to 4 OPA 1678s and one more in the mixer. One to do the mixing and one as a voltage follower for the other channel, just in case. I'm not even sure that's required, but that's how we're going to go, because it seems to work. The only thing of interest here is the output signals were previously all went through a 10K resistor. They're going through another 4.7 here. And then the feedback pot here to control the actual gain of the whole mixed signal at this point is just another 10K. This capacitor should be a 1 nanofarad. I'll go ahead and fill that in now. So you can see my notes here again to myself. Thanks again to Smitty Halibut for showing this. But this is it, the filter calculations at both ends, both extremes of this pop. So if it's producing 1 ohm, this forms a low-pass filter, a high-pass filter, because we need to de-oscillate this op-amp if any high-frequency signals get in there. So at 1 ohm on this resistor, this capacitor will pass anything above 159 megahertz, and it will look like a low impedance feedback source, which will let the op-amp stop oscillating. We'll get that signal back in out of phase on the negative, or in phase on the negative, the inverting input, and cancel itself out, hopefully. At 10K, this will occur at 15 kilohertz, which for this application is absolutely fine. As we discussed earlier, the radio single sideband frequencies end at 3 kilohertz. That number, if you're at all interested, and you haven't run into this already, my understanding is that comes from the old telephone standards, which were all developed by a bunch of older guys who have lower voices. So that's why if you ever hear a violin or a young person or a woman with a high-pitched voice, or anyone with a high-pitched voice, obviously, they tend to sound pretty terrible on the telephone. They'll sound somewhat terrible on single sideband as well, just frequency limitations. But for my voice and for single sideband, 15 kilohertz is just fine. So this filter network should be okay. Another voltage follower for audio out, another decoupling cap, and then we're basically done. Smitty Halibut, again, put 1 ohm resistors in here, and I believe that's just to prevent any shorting. If these got shorted to ground or somewhere, the op-amp in there would attempt very, very hard to bring that voltage up, and that would be unfortunate. It could burn itself out, it could draw down the power supply, all kinds of things. So 1 ohm resistor ensures there's always some impedance to wherever this winds up. And again, to audio out. So, that's the big project I kind of wanted to talk about. I'm not going to do any layout today, but that will be the next step. I just kind of wanted to do a recording for the stream, check out my setup, see how things are working. We'll see how the audio sounds after all this. I expect there to be some noise, and hopefully OBS will provide me with some audio filters or something. I wanted to try out the remotes for OBS, all those things. So a bunch of different stuff. It's interesting. This doesn't tell me how long I've been recording. That's fun. It does tell me I've got plenty of free disk space though. If you have feedback or things you would like to see or suggestions for the stream, either technical of things I did wrong while streaming, or things that I should do, or things you'd like to see me talk about, with the understanding that, hey, I'm new to all this. This is all a hobby. I won't be streaming work, because that's work. Other people pay me for it. And I probably won't be streaming video games, because as much as I love video games, I never find any time for them. I always get wrapped up in stuff like this. So, okay. Oh, goodness. Switch back to the bench here for a final shot. And I appreciate everybody's time. If you've enjoyed this, leave me a thumbs up or leave a comment, even better. I'd love to hear what you think or what you want me to do or not do. Any technical tips for improving my audio, improving my capture, improving my video. I know the webcam I'm using on the bench is terrible and that the angle is terrible. I'm working on both of those. But again, I'm not going to get my Sony camera out and get an HDMI capture card engaged unless I actually find this useful. So, I hope that was useful to everyone, and 73.